And we've been putting out some data, but in about a month, a little over a month, we're going to put out a lot of the main results. So I can show you what we might see, but I can't show you what we'll see because we're bargaining with something. But just watch the newspapers sometime in the March or beginning of April, we'll see that. However, I can show you a little bit of the data. So here is the Planck satellite mapping the sky. The Planck satellite is out rotating around. It's facing the sun and the earth. So here's the sun, here's the earth, the satellite's further out. The combined gravity pulls them along together, it's called Lagrange point 2, and it orbits in exact alignment so that we can always broadcast back to the earth, as it were. And here's the microwaves coming in from the sky to the detectors on board the satellite, and these are actual results coming in. We have 10 different frequency bands, and there are 9 of them displayed here. But what you will see is the sky has a bright white part of it, which is mostly dust in our own galaxy. You'll see we live in a spiral galaxy. It'll be this nice shade across here. And then there's the red behind it, which is the microwave background, and the spots the microwave background. So here's the plate of the galaxy coming across, and you can see we're in the galaxy, so the dust sticks out. This is an optical picture of the galaxy, and this is the picture. Unfortunately, it fades, doesn't stay stuck. But you can see we have to actually understand what signals are coming from our own galaxy. But if you look far away from the galaxy, we're able to see directly out to the universe and do these maps. And from these, so we're going to be publishing these in more detail in just about a month. So there's phone calls and emails many times a day these days. Everybody's trying to get things correct because the deadline is coming soon. And so we have this brief history of the universe. So if we think about that sphere around us, and take a slice through it, and trace that sphere backwards through time, you see the circle, which is the slice through the current sphere, and you see the modern galaxies. And as you go back, you see the size of the sphere changing, but you see the nature of the galaxies changing and so forth. And so one of the things that was a big surprise to us that in 1998 was we found that the universe was not only expanding, which was Hubble found long ago, but instead of slowing down like we'd all assumed, it was starting to go faster and faster. And so that was first noticed in 1998. The data had become clearer, and a year ago, my colleagues were given the Nobel Prize for this discovery that the universe is accelerating. And so that's the first part. We don't know what's causing it. We call that the dark energy, and we're doing studies, and I'll come to it in a minute. We're engaged with some people from Mexico in an experiment to try and learn more about this dark energy. But we know the life history of the Big Bang is 13.7 billion years, and we know the first stars turned on about 400 million years after the universe began. So that's a very early age in terms of a human age. But we were able to make a map back to when the universe was 400,000 years old. So that, in terms of your own lifespan, is about 12 hours after conception. Well, we can actually use the sound waves that we measure in these variations to map even further back into the universe's history to try to understand what's going on. But this gives us a pattern for what's going to happen and what we're going to see next in the universe, which is these galaxies. So while I've been working very hard on measuring the cosmic background radiation, so my colleagues have started other experiments and I'm involved in some of them now. But the first one that was a really big step forward was the Sloan Digital Sky Survey. And in Sloan 1+2, they would map the location in 3 dimensions of over 1 million galaxies. And so 1 million is getting to be noticeable. Now you're starting to you have enough that for each person in Mexico to begin to think about having a star. But wait, they're on a star and on a galaxy. And each galaxy's got 3 planets. So we got a lot to deal with. So why does this picture look this way? It's clearly not random. There's clearly aggregations of galaxies. There's clearly voids where there are no galaxies. And the galaxies fade out. Well, the galaxies fade out because the think there are galaxies further out, and we have some tests where they are there. But what you do is you take pictures like the Hubble telescope, but as the Earth rotates, you take a series of pictures, and you have a cone, which is from the one picture, and that becomes a fan across the sky. So I'm going to show you the geometry of this little digital sky survey. So here it's rotating, and you see the fans. As you look at different places in the sky, you see the fans. So the first thing you see when you look at this, you see the fans. And now you say, well, that's just where we looked. It's supposed to go around again. But you can also see things like along here, there's a big long ridge of galaxies. And we think that ridge of galaxies is actually a wall of galaxies. You see it in the upper left, the stretched part of it. We think it's an actual wall of galaxies. We think it may have as many as 1 million galaxies. So one of the questions we have to ask is how the galaxies come into existence, but how do they also get into this complicated structure? And how likely is it that we happen to be living not so far away from a place, a wall of galaxies? That's sort of a great wall of galaxies. Well, this is not the only survey. So this is the Sloan Digital Sky Survey, but there was a 2-degree field survey, and now we're going to fly through it instead of looking at it. And here you see it's an incredible database. It also has about 1 million galaxies in it. But each galaxy, in both surveys, you have a picture of each galaxy. You know its color, you know its type, you know its location. So you're beginning to start to map the universe. So now we're going to swing outside. We flew down the panel. We'll swing outside and look back. You can see spiral galaxies and elliptical galaxies. And they're roughly equal numbers of spiral elliptical galaxies, but the elliptical galaxies are a little more concentrated in clusters of galaxies. So you can see the wedges here, and you can see these patterns where there are voids and filaments and strings of galaxies and clusters of galaxies. And it gets a little humbling because not only do we not live in the center, of the solar system. The sun's the center solar system. The sun's not the center of the galaxy. Our galaxy's in a small group of galaxies. We're not even in a big group of galaxies. We're nothing special. Right? And there's 4 billion other planets that people could be on, or other things could be on. Okay, so that one goes right. So here's what's in progress right now. Sloan Digital Sky Survey through 3, called, and a big part of the program is called WAS, which stands for Variant Acoustic Oscillations. Those fluctuations we saw in the microwave background in the Part 2000, those are acoustic oscillations from the perturbations that were put in the making of the universe, and they end up leaving their imprint on the galaxies. And that's what we're trying to do. But here's the survey. Now it looks different. You see the big concentration of galaxies nearby, when the telescope's big enough to pick it up. Then you see another ring of galaxies further out, and even further out you see a lot of structures. Why is that? Well, that's because we're now trying to study particular kinds of things. And though we didn't have enough telescope time and so forth to see all that, there are tricks that we can do. And so the trick that's done is you measure 1,000 objects at a time. So you have this big telescope, 2-meter telescope. It's got in it a big focal plane. And you take a picture, you find out what galaxies are that you were interested in. And you put fiber optics in each galaxy, and you run it through a spectrograph, and you measure its properties 1,000 at a time. So this poor person every night has to fill 4 of these plates with 1,000 fibers. So here's what you get when you actually look at the details. So you can see the first surveys in the middle, then we're concentrated in select galaxies that are thought to be a certain distance out. And then further out are some unusual objects. These are mostly quasars. They're very bright nuclei of galaxies that are just getting started. But they give out such bright light that any material that's starting to form into a galaxy that's between you and that, between us and the quasar, absorbs it. And by measuring its spectrum, you can see. So the blue spots that you see there are the actual quasars, and the red line is how it's traced the material until the universe has become completely lumped up. And so that's why that has such an unusual pattern. And we're at the point now where the project has been going on. And so it took 10 years to measure the first 1 million galaxies. Now we're measuring 1 million galaxies per year. And we're hoping to get to at least 5 million galaxies. Then people are debating what to do. But a big group of us have gone to create what we call big boss. Right? This boss and big boss. So it's to do with a much deeper mapping of the universe and galaxies and quasars. And we want to cover at least half the sky from a time when the universe is roughly 1.2 times smaller than it is now. Well, it's 3 times smaller than it is now, so back in the history of the universe. And you see in this little chart, the red is the original volume that I showed you the maps of. The next red is showing you the volume that we're currently getting. And then the next set out there is what's going to be done by a big boss in terms of what's going on. And here we have people from Mexico that are collaborating, participating in this operation. Some of them are here from Mexico City. Okay, so, all right, so it looks very different. Here's the early universe, and I showed you exaggerated math. Remember, the universe is almost perfectly uniform. The variations are part of 100,000. And here's the late universe, and it's all clumped up in the galaxies. Right? What happened? How do you get between those? That's one of the things we have to explain. So the answer is we have to add one more ingredient, which is called dark matter, that literally just clumps up under gravity, and you let it clump up. So I'm going to show you a simulation of this clumping up of gravity, clumping up with gravity, and the universe is expanding, but you keep the box the same size. So the universe is expanding, but you keep the box the same size. So the clumping of the gravity has to fight against the expansion of the universe, but you will see what happens. So this starts with the universe 30 times smaller, and lumps start to form, and then you get filaments. You get structures and filaments until you get down to the present day. Things are sort of isolated and separated. So it's extremely uniform at the beginning. Little peaks form, and then those peaks leak up in filaments. And they give this a shorthand name, the cosmic web, because it kind of looks like a dirty spider web. But this is the framework of dark matter on which we're going to put the ordinary matter, the kind of matter that we see in this room, in order to form the stars and the planets and the galaxies, and eventually the planets and light and so on. Okay, so this next figure, we're going to talk about the distribution. We're going to go from a very large scale, where it looks very uniform, and zoom in to where we see the kind of detail that we were talking about in that simulation. But now the dark matter, instead of is shown in white, the way it was in the last picture, but the ordinary matter, once it forms stars and galaxies, is shown as yellow. So we're going to see the simulation. So this is how it's going to look. So this is a 10 billion particle simulation. This distance across here is 1 gigaparsec. So that distance is roughly 300 billion light years. So now we're down to, 1 billion light years. And we're zooming in. You see this filamentary network. This cosmic web looks much more like a cosmic web. It looks kind of biological to me, but it just has to do with the nature of the way these things fragment. Now we're zooming in on a place where many filaments come together. Where filaments come together, you get clusters of galaxies. Many filaments come together, you get a supercluster of galaxies, or a very large cluster of galaxies. And so this is zooming in to see that. So this is looking at it from above, and as we're zooming in, we're going to eventually get down to the scale where you'll see 2 individual galaxies. That's about how far apart we and Andromeda are. So if we lived in one of these giant clusters, no matter where we looked at the sky with our naked eye, we would see galaxies, right, the way we see stars. But we have to live in a place where we and Andromeda are the 2 big galaxies, and there are several, maybe 40 small galaxies around us. But you basically, they're hard to see with your eye. You can see the Magellanic Cloud if you're far enough south, and that's about all. Okay, now we're going to fly through it. You can see the white is the dark matter, and the yellow, which has fallen to the center, like dirt. You take a bath and the dirt goes to the bottom of the tub. The ordinary matter is able to dissipate and fall to the center of the gravitational wells of the dark matter and form galaxies there. And it's inside of this halo of the dark matter. So this is a picture of what it would look like if you could fly through the universe at great speed and yet still keep the same perspective that you normally do. Because if you go faster than light, things don't look the same. This shows you what kind of thing you can see if you were flying around through